So, okay, so now you're recording the session, right?
Yes.
Okay.
Yeah, so Jorge is now recording it. Good.
Okay, fantastic. So I think you are recording in your computer, right?
Yeah, that's correct.
Okay, fine. Just in case, so I'm gonna do as well. And the point is that we're gonna probably I'm gonna tell Maria Jose Calderon that we are recording the session, and probably she will ask us later on to send to her the recording. Okay. So I think that Jose Luis, have you fixed the problem with the?
I think so. Now you can hear me.
Okay, perfect. Yeah. So now because you are a co-host, you have the option to share screen. Right?
Yeah.
So can you share your screen with a presentation, your presentation on all the presentation, just to see that everything works properly, please?
Yeah. Give me a minute, please. Now you should see it.
Okay, can you put the full screen mode, please? Okay,
No?
perfect.
Okay, perfect.
Thank you. So then, so just as a reminder, all of the speakers of today's session are co-hosts. So it means that all of them can share their screens at any moment. It also means that if they are not the speakers at this moment, they can interrupt the talk of the current speaker. So please, I strongly recommend to turn the speaker off and not to share screen if it's not necessary. Okay. So I think it's still 15 minutes to, and the rest of the participants will start with the camera and the speaker off. Okay. Also, let me remind you that one of the organizers should be looking who is in the waiting room, and the other is ready for controlling the time of the session, right? For instance, just reading if there are questions, that question will be posted in the chat, okay? And at the end of the talk, there is time for reading the questions. I think we discussed this during the testing session. If there is something any question or any comment or complaint, so we still have 15 minutes to.
Yeah, well, anyway, we were planning to start a bit later, like 15 to 10, because actually introductory talk doesn't have so much content. It's just some general comments and some indications also for the public. But that's it. I have been having some issues this morning to log in the website. So I actually have to ask Mario to send me the link himself.
Really?
Because, yeah.
I think they're gonna send.
Several tries I didn't.
We got an email earlier, I think was either this morning or late last evening, with all the links for the sessions of this morning. But I managed to load the website here with no problems.
I think the idea is that yesterday or today, early in the morning, they're gonna release the links for today for the all sessions, also for the plenary talks and the invited talks, and they're gonna do this for one day in advance. So today, later on or tomorrow morning, they're gonna release the links for tomorrow and so on.
Yeah, I did get them. Yes. So also the email yesterday, quite late probably. Yeah,
probably this quite later on they're gonna release the links for tomorrow. Also, something I didn't say, I think last time, is that the session formally ends at 12:30, right? But the session is open till 13:30. 1 o'clock in the and 30. So just in case you want to discuss just to, if there is some kind of discussion or something like this. Okay, because this is not a session, or it's not, this session is not held by a Zoom account that is going to be used later on in the afternoon. I think there is no problem. So you are still here till 1:30. So I do not promise to be here at that time because I have 2 kids to take care of.
Okay.
I think, Mario, is there one of the speakers that has not tested yet the microphone, the speakers, and no? I think everyone.
Yeah, I think pretty much everyone has done it. Yeah.
Okay, fantastic.
So for the shake of clarity again, so we have to tell everyone, or everyone will log in with the cameras off and muted, and we have to do it as well, even the co-hosts and chairmans or whatever, or chairwoman or whatever we have. It's only the speaker who is getting camera. Is it? No? Yes?
So do you agree with this?
I don't know. I mean, it's I don't know what's the policy exactly. So
okay, the story is that the general policy of the organizer is just that all the audience should have the camera off and the speaker off. Yeah. The speakers is recommended, but it's up to them. Because there is the option of, I mean, you as a chairman, you have the option of fix the camera or the video of the speakers. Okay. So when, for instance, who is the first? Jorge is the first who is going to talk, right? So we can fix the video to him, right?
Okay.
There is an option. I mean, if you put the arrow on top of his camera or his image in the three spots in the upper left corner, there is the option of fix the video or fix.
You mean like this, right?
Or spotlight.
I think I just did it.
So no matter if I'm talking, we are all looking at him. If we do that systematically for all the speakers, it doesn't matter too much if we all the other speakers have the camera off. It's also important if you have if you're using Wi-Fi or something like this. So if, I mean, turning off all the cameras and speakers just reduces the information that is streaming, that is being streamed. Also, I do recommend Mario or Jorge, the one who is going to be chair, just to take the camera on, because in this way you can make some kind of visual or some kind of control of the session.
Yeah, but anyway, the speaker is not going to see our faces, right?
Well, I think, well, that's depend on the view he or she's using. For instance, in the upper right corner, left right corner, there is the option view gallery or face to face or side by side or something like this. I think that depends on the option you're using. You see just one face or your face, or all the faces that all the people that have the camera on. This is another reason to get the camera off as much as possible. So for instance, now Jorge, okay. So now Jorge has the spotlight. So the point is that you have to go one by one in the speakers to change this option.
Sorry, what do you mean?
So I mean, what you did is just to fix, or I don't know how.
So you mean that I'm the only one allowed to use this spotlight feature, right?
No, I mean all the co-hosts can do, I think.
Okay.
But the question is that I suggest one of the organizers, one of the chairmans, to do systematically go.
But now in my video, it keeps hopping between you and Jorge, actually, depending on who is speaking. So I think that the spotlight video is just that it's gonna show whoever is speaking is gonna show.
No, right now it's disabled. So when I turn it, I can turn it on, for example, now.
Yeah, I did it for you.
Now if someone else speaks, you should still see me.
Can somebody try? Nobody is speaking.
Can anyone speak, please?
Hello, 1, 2, 1, 2. Hello. Hi, everyone. Hi, Andres. Okay, let's big wave of hands today.
I think it's yeah. Now I only see Jorge.
Okay.
Okay, then that works.
It's much better.
I just turned it on.
So, good.
Anyway, so at 9:30, I will just leave a note in the. So I will share my screen with a slide just indicating that we start at 9:45. Yeah, so at that point I will start with my.
So another question: the schedule is as in the program, right? So Jorge is the first speaking, right? Then Marcos, Carmen, Daniel, Andres, Sergio, and Pedro, right?
Yeah, that's correct.
So this is the order that is gonna keep maintained, right?
Yeah.
Okay, good, thanks.
So we start then at 15 to 10, right? Is that right?
Yeah, well, quarter to 10, yes.
Quarter
probably.
to 10, yeah.
Yes.
Okay, thank you. So I will
go for a coffee, yeah, enjoy.
I will prepare a coffee, that's right.
I think I will do the same.
Cheers.
So Mario, sorry, there is someone in the waiting room with no name.
Yeah, and
so
I will
think
ask directly. Sorry.
No, that's fine. So the point is that it's strongly recommended to write their names on any recognizable name, just to be sure that we know each other. I'm gonna ask him.
Yeah, I'm doing it now.
Okay.
Okay, good morning, everyone. My name is Jorge Quereda. I'm going to be one of the hosts of this session. Let me start with a brief introduction of the session. So, as you know, the session is titled Symmetry and Non-linearity in two-dimensional in nanosystems. We will have a large session, especially in the first day, about two-dimensional systems and van der Waals materials. Then we will have also a second session about other systems, and in particular about nonlinear transport in a series of different systems. And finally, we will finish tomorrow with a short session about CIS, chirality-induced spin selectivity. Just a few comments for those of you that are not aware of them. So for attendance, well, you are requested to keep your microphone and camera closed at all times. Anyway, we will have control of this by yourselves, so you don't have to do anything about it. Please feel free to ask questions through the chat during the talks, and these questions will be read and answered at the end of the talk. So my co-host Maria Amado, which is the other organizer of this meeting, will be reading the chat and moderating the questions at the end of each talk. You can also, if you want, send private messages to the speaker using the chat. And also in that direction, we have just been notified that after the session is over, so at 12:30, the chat room will still be open for one more hour until 1:30. So that's a good place to have conversations later if there's some question that is still open. Also for speakers, please remember that you have to share your screen when you start your presentation, and you have to unshare it at the end of your talk. And you're also requested to please not share your screen at any other time, because otherwise you will interrupt the presentation of whoever is talking at that point. Also remember that the session is being recorded, so whatever shows up in your screen will be recorded as well, so be careful about notifications that appear there or anything that could be delicate information. Also, we have been requested that we stick very strictly to the time slot. So I will let you know when there are 2 minutes left before the end of your time, so you can give your final conclusions. And then we will have some time for questions, and we'll go for the next speaker. But we are requested to be very strict, because this way the attendants can jump from one of the mini-colloquia to another one if they are interested in specific talks. Finally, for everyone, for the rest of the sessions, you should have received an email. But anyway, in case you didn't, then there's this link which you can use to access the plenary and semi-plenary sessions of this conference. So without further ado, I will give the floor to our first speaker, which is Marcos Imarez. Marcos, are you around?
Yes, I'm here.
Okay, so Marcos is working in the optospintronics of nanostructures group in the University of Groningen. It's a very young group from which he's the group leader. So, okay, Marcos, I will stop sharing the screen, and the floor is yours.
Let me start here. I think you probably can see my screen right now.
Yeah.
Right? So thanks for the invitation, and thanks for the introduction, Jorge. It's an honor for me to be the first speaker in this session, and the first speaker of the conference here. So it's pretty nice. I would prefer to be in Madrid right now. I think the weather is much better over there, but well, it's nice to be able to present the work here for you today. I'm gonna show a work that we've been doing for a while now. We started at Cornell, so I would like to thank especially Dave McNeil and Greg Steele, who together with me initiated this project on exploring spin orbit torques using 2D or Van der Waals materials. Then later on, I continued this work at Eindhoven, and I have to give special thanks to Casper Schippers, who was a PhD there, that during my time in Eindhoven, he helped me a lot with this project. So I'm gonna just go briefly through spin orbit torques. What are spin orbit torques, and why we should care about it? Why they're important? And then later on, I will give a few examples. It's kind of a build up from starting from 2017 on tungsten ditelluride, and then move to niobium diselenide, and then finally our latest work on nickel thiophosphate, which is a Van der Waals insulating antiferromagnet. So what are spin orbit torques, and why should we care for spin electronics? I think a few of you already know that there is a new type of RAM memory, a magnetic RAM memory, which is non-volatile, that uses spin transfer torque. And these memories are already in the market, so you can buy and put in your computer, and they give it a way that if you turn off your computer or turn it on, the information stays in the RAM, which is different than the RAM that we use nowadays, SD-RAM, for example. And these spin transfer torque RAMs, they work with the memory cell is basically a magnetic tunnel junction, which means that we have a magnetic layer, well, two magnetic layers separated by an insulating barrier. And then we can read and write information by flowing the current through it. And the resistance is high if these layers are pointing with a magnetization anti-parallel, so one pointing to the right, let's say, the other one pointing to the left. This converts into a bit zero. But if we drive a high current through this barrier, through this stack, then we can switch between 0 and 1, so between parallel and anti-parallel, and this is how we write the bit. And if we drive a smaller current, that's how we read the bit. But the problem is that these barriers are very, very fragile, and they break very easily. So we only have a few times of read and write before the memory cell degrades. For that, there's been a recent development in the field which uses spin orbit torque combined with this magnetic tunnel junction, in which we separate the read and write line. So the read line is here, vertical, so that's, we drive a small current, so this doesn't damage the barrier, but the write line is separated into a big pad underneath the free layer, the layer that we can switch the magnetization. And this write line works as following. We drive a current through, a regular charge current, and because of some spin scattering mechanism or some sort of spin orbit coupling effect, then we separate spin up and spin down from these currents, and we can, for example, inject spins with one direction into the free layer, and they apply a torque on the magnetization and eventually can switch it. There are several advantages of the spin orbit torque MRAM over the STT MRAM. Is that, well, it's efficient, it's non-volatile, that's because it's magnetic as the STT MRAM, but this is an advantage over the standard RAM memory that we use in our computers, and it's fast. So it can be used the same way that we use the SD RAM. And for increasing the efficiency here, we need to have this write line needs to be composed of materials which show high spin orbit coupling and this converts into a high spin torque efficiency. And one way to create this separation of spin up and spin down is through the well-known spin Hall effect, in which you have high spin orbit coupling material attached to a ferromagnet. And if you drive a charge current, you have electrons with, let's say, spin up and spin down here. And the spin up electrons are deflected to the top part of the layer. They get absorbed by the magnetization, by the magnetic layer, and apply torque on this magnetization because of conservation of angular momentum. And we can quantify, so we can write down that the spin current density Js equals the spin Hall angle, which is the efficiency, times the charge current density. And the standard in the field now, and also what's being used to develop the SOTM ramps, is platinum. And platinum has an efficiency of about 10%, which is pretty low. So this has been a drive in the field now to find systems which show more efficient conversion from a charge current into to a spin torque, and also different mechanisms. Because one thing that spin Hall effect doesn't give you is a very efficient way to switch out of plane magnetization, which is used in the modern magnetic technology. And it turns out that layer materials are actually pretty interesting for that. So I think many of you know that you have a huge family of layered van der Waals materials. You can stack them up here as shown in this image, and you can have graphene, which is kind of a metal, which is maybe the most well-known, and then the second most well-known is maybe boron nitride, which is a very good insulator. But you also have semiconductors like molybdenum disulfide, and you can have all a huge amount of properties, different properties like superconductors, semi-metals, topological insulators, so on and so forth. And the main advantages of these materials is that, well, because of their large family, we can have many different properties, right? So with the same, with similar systems, we can tune the resistivity, we can change the band gap, we can change the crystal symmetries, which turns out that is going to be very important, as I will show later on. And they're easy to exfoliate and get atomically flat single crystals, which is important to the study of the symmetries and the impact of the symmetries on the spin orbit torques. And they can give you a large degree of values for the spin orbit coupling. However, there are a few disadvantages, and those are that many of the interesting materials are air unstable, so we need to work with care. The growth and the processing is often not compatible with CMOS processes, but there's a lot of effort in this direction. I won't go into details, but we are getting closer and closer to that. It's pretty difficult to grow in wafer scales, but again, there are many groups doing an excellent job over there. And the single crystals are not available in a wafer scale yet. So for this reason, we use mostly exfoliated materials because, well, we are experimental physicists in the lab. We just want a proof of principle, so that is good enough. But what are spin orbit torques, and what are the symmetries here? So it comes from a very basic ferromagnetic resonance nomenclature, in which we have a magnetic layer with a magnetization pointing in this direction here. And if we apply a magnetic field that is non-collinear with a magnetization, what happens is that this magnetic moment starts to precess around the magnetic field, right? And this, because the change in magnetic moment with time is a torque, this gives a torque in this direction, which is tangential to the the precession orbit over here. So this is called a field torque. But this can't stay forever, and eventually the magnetization will align to the magnetic field, and this is because of a damping mechanism. And this gives a torque, so this converts into a torque that is pointing towards the magnetic, towards aligning the magnetization with the magnetic field here, which will damp out this precession. And if you write down into a mathematical equation, you get that this field-like torque, it can be written as the magnetization direction m cross product with a certain direction, which is the field direction. So in this case, let's say x. Right, so it would be an m cross x. And very important here to keep in mind is that this type of torque is odd in the magnetization direction. So this means that if we change the magnetization, go from plus m to minus m, the torque also changes sign. The second term here, which is this damping torque or damping-like torque, is even in the magnetization direction. So if we change m to minus m, the torque doesn't change sign. And it's given by an m cross sigma. Sigma here is x, y, z, the direction of the field. So let's say x again, so m cross x cross m. So how do we measure spin orbit torque? Here I'm bringing up our basic memory cell there from our SOT MRAM. And we are going to use just the bottom part here, just below the barrier. So we have the spin orbit material, so a right line, and the free layer. And it looks like this. So we have the spin orbit material underneath the ferromagnet. Now, if this ferromagnet has a magnetization M here pointing in a certain direction, and we drive a current through this material. This current has a magnetic field associated to it, which is called the Oersted field, and this is basic electrodynamics. That if you have a current, you have a magnetic field associated to it that circles around, and this causes a torque for a magnetization that points in the plane that causes a torque out of plane. And again, this can be converted into an M cross Y term, and this is mostly due to this Oersted field. Now, if we have, for example, spin Hall effect, the spins will be entering, pointing in the plane because of conservation of angular momentum. This wants to displace the magnetization in the plane, which causes an in-plane torque. And here we can write down the torque as constant, so this tau parallel, an M cross Y, and Y here is the direction of the spin. And this torque is even in a magnetization direction. Now, how do we read the torques? We read using AMR, which can convert the angle of the magnetization, the angle that the magnetization makes with the current, into a changing resistance. So as we apply the current, this current applies a torque in our magnetization, and this torque makes the magnetization change its angle with respect to the current, and then we can read the resistance. We can read this angle through the resistance of the device. One important method that was developed is a resonant method, which uses ferromagnetic resonance to read the torques. This is called spin torque ferromagnetic resonance. And here we apply an RF current, so a current in the gigahertz range, through, so it passes here through a signal pad, and the connection between the signal pad and the ground pad, you have or stack there that could be, for example, platinum and a ferromagnet like permalloy. And when the frequency of this RF current matches the frequency, the Larmor precession frequency given by an given by an external magnetic field, Then we have a resonance condition. And this we can read through a lock-in amplifier. We read the voltage as a function of applied magnetic field for a fixed applied RF current frequency. So when the frequency of this current, when the frequency, the Lyman precession frequency given by the magnetic field matches the frequency of the current, we have a resonance line in our voltage detection that looks more or less like this. And this shape is actually pretty nice because you can decompose into two components. So a symmetric Lorentzian that looks like this in blue, and an antisymmetric Lorentzian that looks like this in red. And they give you direct information on the torque. So the antisymmetric Lorentzian gives you something that's proportional to the derivative of the resistance with respect to the angle of the magnetization, the current that you're applying, but most importantly, this antisymmetric component is proportional to the out of plane torques, which, if you recall, it is mostly proportional to the worsted field, for example, given by the current. Now, the symmetric component is proportional to the in-plane torques that, for example, could be due to the spin Hall effect. Very nicely, if you do the ratio of these two, the amplitudes of these two signals, then you directly get the spin Hall efficiency. So it's a very easy method to directly measure the spin Hall efficiency. But as I told you before, the spin Hall effect and platinum are not very nice systems to get nice spin Hall spin orbit torques because the symmetry is not quite right and the efficiency is not quite high. So can we use single crystals of 2D materials to control the symmetries of the spin orbit torques? That's the question that I'm going to try to answer here to you. So if you take the basic system, the standard in the field, platinum and permalloy. Permalloy is a ferromagnet. Platinum is your spin orbit metal. You apply an electric field or a current through it, and you have the magnetization, let's say, pointing at 40 degrees with respect to the current that you apply. This is fixed by an external magnetic field H. Now, if you reverse the magnetic field, the magnetization will reverse. And what you get up to a minus sign is that the resonance shape from the spin torque ferromagnetic resonance for a fixed frequency looks like this. So if I apply the magnetic field at 40 degrees, you can see here in red. And if I reverse the magnetic field, so now apply it to 20 degrees, then that's the curve in black. And they overlap. They fall exactly on top of each other. But now what happens if you use a material that has a lower symmetry, for example, tungsten ditelluride? So now we have a tungsten ditelluride with a ferromagnet on top, and we do the same trick. So we apply the magnetic field in a certain direction, measure the STFMR response, reverse the magnetic field, and measure the STFMR response again. And now they look completely different. So as you can see here, the black line, which is with the field applied in a certain direction, and the red line, which is the field applied in the opposite direction, they're very, very different. And this, it turns out that it can be explained by a torque that is an even torque. So it's a damping-like torque on an anti-damping torque. Which points out of plane, and it has the form M cross Z. And this torque is a very special, and it comes directly from the symmetries. You can understand that its presence from the symmetries of the tungsten ditelluride. So let's recap the symmetries of the crystal. So of course you have the identity, which leaves everything into place. You have a mirror plane here. Which is in the b-axis, along the b-axis of the crystal, you have a glide mirror, which is along the AC plane, plus a translation in the X and Z direction. And you have a screw axis, which is a C2 rotation and a translation in the X and Z direction. However, and this converts into a space group for the people that like group theory, PMN21. However, now if you couple with a ferromagnet, so we put the ferromagnet there on top of this tungsten ditelluride, we reduce the symmetries. So we lose all the translations that we had, which will make a translation in the Z direction, just because now we have this interface over there. And this reduces the symmetry operations just to the identity and the mirror plane, which is along, which is at the BC plane. And this has space group PM. So now if we map the antisymmetric component of that resonance curve as a function of the angle of the magnetization, then you can see that it has this funky behavior. And this can be explained by, as I told you, by the symmetries of the tungsten ditelluride. So the fact that this dip here just after, so at around 220 is not the same amplitude at the dip in the minus 45. This is due to that out of plane anti-damping torque. And now let's look at the symmetries of the crystal now for with the torque included. So we have the current flowing parallel to this mirror plane, and let's say that it causes a torque that points out of the plane here. Now, if you apply the mirror plane, the current stays the same, but the torque is a pseudo vector, so it has to reverse sign upon a mirror plane. And this tells you, so since the torque is linear in current, this tells you that the torque has to be zero by symmetry. However, if we apply the current now perpendicular to this mirror plane, when we apply this mirror plane, we reverse both the torque and the current. So what symmetry analysis tells you is that a torque pointing out of the plane is allowed. It doesn't tell you if it is present, but it only tells you that is allowed. So one thing that I didn't tell you is that this torque is actually ideal for the out of plane magnetization switching. So it would be ideal to have those incorporated in high density SOT MRAMs. So this is the type of torques that we are looking for, which are not present in platinum. Now we can also make many devices with different angles between the current and the mirror plane. So each point here is a different device. And if you go with the current parallel to the mirror plane, you can see that you have actually this is opposite way. If the current is perpendicular to the mirror plane, we have a large torque intensity, and as we go to the current more and more parallel to the mirror plane, then we have then this torque goes to zero, as we would expect from a symmetry analysis. But how does it size up? So we have platinum there that has a spin Hall efficiency of about 10%. And tungsten ditelluride for these special torques, the efficiency is actually pretty low, it's about 1%. And the spin Hall-like torque, so the same type or same symmetry as the platinum, has about 2%. So it's pretty low. The young group in Singapore found out that you get more efficient torques for thicker tungsten ditelluride and can get closer to platinum. But one of the reasons why the torques are a little bit inefficient is because tungsten ditelluride is very resistive. So it's a semi-metal, but it points in the right direction, that we can control the torques with symmetries of the crystal. So what happens if we go to a metallic system? So we leave tungsten ditelluride, which is a low symmetry system and semi-metal, and we go to niobium diselenide, which is hexagonal and metallic. It also has a higher spin-orbit coupling, in addition to have the higher conductivity. So we played the same trick. Now STFMR on a niobium diselenide permalloy, measuring the STFMR over there curve, and down to a monolayer of niobium diselenide, we see a strong spin-orbit torque response. However, if we do the same thing, we reverse the magnetization direction, you can see here that that the curves are also very different. But this is actually not allowed for a hexagonal lattice. So what's going on there? So we add one more layer, and you can see that if we do the same thing for a bilayer device, the curves are a little bit more similar. And we can do the full angular sweep there, and you can see that for the symmetric component now, for the monolayer is very different than the bilayer, while the antisymmetric looks more or less the same. And this would be consistent with the presence of now an odd torque, so a field-like torque, M cross Z, which again is not allowed in the platinum devices because of symmetry. It shouldn't be allowed in niobium diselenide also because of symmetry. So there's something else going on there. So we did a thickness dependence going from monolayer, bilayer, 4 layers, and so on and so forth. And then we can map the torque intensity as a function of the thickness of the niobium diselenide. We start with a simple Oersted field-like torque, M cross Y. And this dashed line here is what you would expect from the Oersted field torques from the current flowing through the niobium diselenide. But if you look closely, for a monolayer and bilayer, they fall significantly below our error margin. And for monolayer, even points in the opposite direction. And this is a strong indication that these torques are actually coming from the interface between the niobium diselenide and the ferromagnet. Now, if you look at the spin Hall-like torque, M cross Y torque, look the intensity as a function of niobium diselenide thickness, looks more or less constant there for lower thickness, and maybe it increases a little bit at the higher thickness, indicating that we have the presence of both an interfacial torque and some bulk effect-like. So it would be kind of a Rashba-Edelstein plus a spin Hall effect. But now this weird torque, the M cross Z torque, which is not allowed by symmetry, is basically all over the place as a function of thickness. So this got us thinking. And if we do a simple symmetry analysis, if we look from the top there of the crystal lattice, this torque has to be 0 by symmetry. But if we distort it, if we distort the lattice a little by strain, for example, this torque becomes allowed, and this means that it would give us a way to control spin-orbit torque through strain, which is something that we are planning to.
Minutes left. Sorry.
Okay. Yeah. Thanks. Which gives us a nice way to control the torques. Another way that would be possible is using magnetic control. So if you look at niobium, at nickel thiophosphate, which is a semiconductor, so it has a large, relatively large band gap, so it's basically insulating for all purposes. It's a little bit air unstable, but we can work with it. And the neo temperature, we can cross it's going from room temperature down to liquid nitrogen temperatures, is around 170 K. And it gives a nice magnetic pattern like that. So I won't go into details. We measure the torques with a slightly different approach, but it's a non-resonant technique, but we can extract the torques nonetheless. So if you look at the field-like torque, now this is the torque that looks like an Oersted field, but you have to remember there is no current going through the nickel thiophosphate because it's so resistive. And the torque intensity as a function of temperature here, it looks like there is a temperature dependence. And it varies from device to device. It can even change sign. And well, it's below the platinum. So here you can see in the green stars, you have platinum permalloy. It's much below that just because, well, we have no current going through. And this gives you a direct indication that these torques are interfacial. And the sample-to-sample variation here can be expected because of the different scattering properties of the interface between different devices. Now, very interestingly, the damping-like torque, the M cross Y, which is the spin Hall effect-like torque, depends much strongly with temperature but the response is different from device to device. But now if you compare to the field standard platinum permalloy, then we have something that at low temperatures is much stronger than platinum. So we have an interfacial torque that is much more efficient than the standard in the field. Now let's look if there is any symmetry dependence. As we cross down the neo temperature, we have a change in the space group. And if we apply the current in different directions, or apply the current in one direction, we get the torque efficiency as a function of temperature for the field-like torque. If you apply the current 90 degrees oriented to it, then we have a small change, and this doesn't seem to change much as we cross the neo temperature indicated in the dashed line here. If you look at the anti-damping-like torque, this has a little bit of stronger difference, but still we don't see very strong indication that the magnetic field, the magnetization is playing a role there. So we have to explore this a little bit better. So what we know so far, so the spin orbit torque symmetries, here, all the symmetries there. For platinum, we just have the standard out-of-plane field-like and the in-plane anti-damping-like torque. The others are not allowed by symmetry. For the tungsten ditelluride, we observe the out-of-plane anti-damping, but not the in-plane field-like torque, even though symmetry allows. The niobium diselenite, I should say strained niobium diselenite, is actually the other way around. We observe the in-plane field-like, but not the anti-damping out-of-plane torque. And the nickel thiophosphate, we observe neither, even though they are allowed below the neo temperature. But this gives you that. So I hope that I convinced that that layer materials are promising candidates for high efficiency spin orbit torques with the different symmetries. And we need to understand a little bit better the mechanisms involved to see which torques are allowed and which torques are present in the various systems that we studied. With that, I would like to thank my collaborators once again, and thank you for your attention.
Okay, thank you very much, Marcos. So Mario, I don't know if there's any question in the chat for Marcos.
So there is none for the moment that I'm aware. So please, if you have any question, can you please just write down in the chat, and I will just.
Oh, in the meanwhile, I have a question myself. So Marcos, you, yeah, when you were discussing about the symmetries of 3D materials, you were saying that when you put them together with permalloy, the symmetries are reduced, right? But I guess that reduction, even if just by looking at the picture, it looks like they are reduced. It depends on how strong is the interaction between the permalloy and the 2D crystal, right?
So
can you comment on that?
I cheated a little bit because in principle, at the interface, these symmetries are already reduced. Right, so in principle, you don't need to have the permalloy there. If you just look at the crystal that is like that, for example, a bilayer device, then these symmetries will already be small. Right, you already lose the translation in the z direction.
Okay, just because you have an interface in there. But then you have
just
an effect also in the bottom interface, right?
Yeah. So I mean, you have here is even stronger because you have the substrate on one side and the permalloy on the other. But in principle, you don't need to have this permalloy actually to measure something that is similar to what we measured in tungsten ditelluride. And this was shown by Pablo Airo and Kinfei Mak last year, if I recall correctly. They shown the nonlinear Hall effect in tungsten ditelluride, and this is consistent with what we measure here.
I see. And then also the fluctuations between one device to another one could probably be explained by this, no? The quality of the interface should very strongly affect what you see, right?
Yes, that's true. I mean, the spin-orbit torques, they will be affected quite a lot from the spin transparency through the interface. So, you, for example, spin Hall effect. One naive way to think about it is that if you create spins on the tungsten ditelluride, you need to transmit them into the ferromagnet, and if this interface is very bad, then the spins cannot go through. Okay. So it is very difficult to make these type of devices, as I think you know. So it's sometimes we do get poor interface qualities.
Okay.
Yeah, we have a question here. Does the speaker expect any renormalization effect in this spin torque signals like electron magnum?
It's a difficult question. So in principle, we treat everything as there is no strong interaction, I should say, between the spin orbit material and the ferromagnet. Of course, that at the interface there, especially, you have you can't discard, for example, the exchange fields, and this could cause indeed some change in your spin orbit torques. But so far, I have to say that we didn't observe anything in this direction, also because the damping of permalloy is still relatively large if you compare to, for example, YIG. So the magnons are not, they don't live for a long time there. And this is part of the answer. I hope it answered the question.
Oh yeah, I think so. Thank you.
Okay, so if we do not have any more questions, maybe we can leave a minute in case anyone is typing right now, and then we can change for the next speaker. Okay, I think we can change. So thank you very much, Marcos. Yeah, thanks for answering. Next up, we have Carmen Maya Giraldoni. She is a PhD student at the University of Groningen at the Group of Quantum Devices. So Carmen, please, the screen is yours in this case, not the floor. Carmen? Carmen, we can see your screen, but we cannot hear you.
Yes, you can hear me now?
Yeah, now it works.
Yeah, okay, great. Thank you very much, Jorge, for the introduction. Thank you, the organizers for giving me the chance to speak here. Today, I'll talk to you about the work I've been doing in the past year or so at the University of Groningen with Marcos, Freddy, and Casper on the symmetry of spin scattering processes in TMDs. So it's
sorry to interrupt, but we cannot see you. I don't know if you have to turn on your video as well.
I can't figure out how to turn my video with the talk already on. Start my video. Okay, great. Does that work?
Let me see. Can you talk to see if you
Yes, yes.
Yeah, okay, now we can see you. Okay.
You see me? Yeah, great.
That's it. All right.
Yeah, okay. So like I was saying, it's not any news for most of you, I guess, that transition metal dichalcogenides, especially the few layer systems, are very interesting for spintronic device applications. And Marcos has just given a lot of examples of why that is so. The reasons for that is that the charge carriers in these materials, they sit in bands that are spin valley coupled, and that provides us with various degrees of freedom in order to control the states of these charge carriers. Also, the direction of the spin in these materials is locked by the symmetry and spin orbit coupling, and that leads to very long spin lifetimes. Finally, we know that the optical selection rules for exciton creation in these materials is spin polarized, right? So spins of different species talk to light of different polarization. So that also gives us an optical knob to create spin accumulation and spin polarization in these systems. So all of these properties that I just mentioned, and also like Marcos just highlighted, they arise from the particular symmetries of these crystals. And we know that we can manipulate these symmetries in various ways. So we can either do it intrinsically by changing the chemical structure of the material, but we can also do it extrinsically by stacking different layers of different materials on top of each other, or by applying strain. In fact, Andres Castellanos will be speaking later today. He has plenty of very nice, beautiful work on the effect of strain in these materials. For me, coming from a spintronic perspective, what I'm interested in is how can we change the symmetries, or how can we manipulate the symmetries in order to extend the favorable spin properties, or to be able to manipulate the spin polarization in these systems. And I do that purely from a group theoretical perspective, right? So my big question here is, what can we learn about the different spin scattering processes in these materials based purely on the group theory? And how I will do that is, first of all, I will look at the symmetry of the eigenstates at the k and k prime point. And then based on these symmetries, I will obtain the selection rules for spin scattering mechanisms, right? So what kind of operators can actually cause a spin to flip in these states? So if I want to start by looking at the symmetry of the eigenstates at the k and k prime points, all the ingredients I need are actually here, right? These TMDs, they have a lattice structure that is hexagonal, like many of you know, and it's shown here. And the symmetry of this lattice at the k and k prime point is actually given by this C3H point group. And this is the point group that I will use from now to the end of the talk to obtain this selection rules that I mentioned. Also, we know from tight binding calculations and from DFT that around the k and k prime points, so where all of the low energy physics happens, the wave functions are mainly composed of d orbitals of the transition metal atoms. So for the conduction band, these wave functions are formed by these dz square orbitals. These are orbitals that don't have any orbital angular momentum, and that is emphasized by the fact that if you think of the color with which I plot these orbitals here as the azimuthal phase, so the phase winding in the plane, you can see that this phase is constant for the dz square orbitals. Now for the valence band, these wave functions are mainly composed of dxy and dx squared minus y squared wave functions that can actually combine. So we can form linear combinations of these wave functions, and we combine them symmetrically or anti-symmetrically. And these two different linear combinations actually do have an azimuthal phase that winds in opposite directions. So these wave functions are actually orbitals with orbital angular momentum plus and minus 2. So given all of these ingredients, I can now try to figure out what is the symmetry of the Bloch wave functions that are delocalized along the entire crystal. Right? And here, what I do is I plot the orbitals in a schematic of the real space lattice, where, again, the color is the phase of this orbital, and it's given by this, this scale over here. And what you can see is that they are actually quite different. And the difference I want to point out is that the wave functions in the conduction band, they have a phase when going from one atom to the other, right? So if we classify these wave functions based on the irreducible representations of the C3H point group, so that is just a classification that tells us how these wave functions transform. Well, they actually transform as the E prime irreducible representation of this C3H point. Now, for the valence band wave functions, you can see that although they have a phase within each atom, if you go from one atom site into the other, the phase is constant, right? There is no phase acquired when you do that. So that means that the valence band wave functions actually transform as the fully symmetric irreducible representation A prime. But that's not the entire story because, well, these charge carriers also have a spin, and spins transform in a very particular manner. So if we go on with this approach and we try to figure out the symmetries of these wave functions, and we take into account how these spins transform, what we obtain is this band structure that is probably very familiar to all of you, right? Indeed, we can observe here that we have this spin valley coupling. That's not anything that is new. And I classify these wave functions based on the irreducible representations that they transform according to, again. And these ERAPs are now given by the subscripted K. Now, what you can notice also is that there is a splitting between the two spin subbands, both in the conduction band and in the valence band. And this splitting is much larger in the valence band than it is in the conduction band. And that you can understand again from this representation of the Bloch wave functions. Right? So like I told you, in the valence band, there's an orbital angular momentum around each atom coming from the atomic wave functions. And this large orbital angular momentum actually gives rise to this large spin-orbit coupling. Now, like I mentioned also before, I'm mainly interested here in low energy processes, so processes that we would observe in transport. And for that reason, since this splitting in the valence band is so large, I will from now on disregard these lower levels here. Also, from now on, because I'm interested in the symmetry of these states really at the edge of the bands, I will represent them as states rather than bands. And what I want you to notice, although I have written down all the ERAPs explicitly, the only thing you need to remember is that these states that I circled in green, they transform as states with photo angular momentum plus or minus 3/2. Whereas the states that I circled in orange transform as wave functions with angular momentum plus or minus 1/2. So this gives us now all the symmetries that we need to figure out the selection rules. I need to tell you that the ordering of these states, I think also most of you know, that depends on the particular transition method that chalcogenize that you take into account. And the ordering that I have drawn up here actually corresponds to tungsten disulfide or tungsten diselenide. But although the ordering does depend on the particular TMD, the symmetries do not. So now that we have these symmetries, what can we learn about the spin flipping transitions? Right? If we just look at a product table for the C3H point group, we can figure out that only operators that transform as E double prime can actually cause spins to flip in these materials. Now we can also go and check what type of operators are those, and that is actually a magnetic field in the plane of the monolayer. So only magnetic fields in this plane are actually able to flip the spin. What you should notice also is that I drew no arrow here between K11 and K12, and that is because since these states are each other's time reversal symmetric, there's no scattering allowed between them. This scattering is protected from time reversal symmetry. And that actually matches very well some recent experimental results in this work that was recently just this summer published at ACS Nano, where they look at up and down conversion processes between the various excitant species. And what they find is that they see no evidence, although they see various conversion processes going on, they never see any evidence of this conversion process that I highlight here with this arrow, where we transform a bright excitant into an inter-valley bright excitant, actually. So this is very much in line with our conclusion here that this scattering is protected by time reversal symmetry. So for this first part, what I need you to take home is that the symmetry of the wave functions in the conduction band and in the valence band are very different. And that actually leads to different scattering processes for electrons and for holes. Also, if you look at this table and you look at the electric fields, there's no spin flipping process that is provided by an electric field for a monolayer TMD. Right? So they should be quite robust with respect to the presence of local electric fields. Now, what happens when we look at the bilayer? Strictly speaking, the main difference in symmetry between a bilayer and a monolayer is that the bilayer has this inversion point over here. And that would mean that we cannot observe any spin valley coupling for bilayers. However, it's been proposed theoretically already a few years ago and shown for various systems that even in systems with inversion symmetry, sometimes something called a hidden spin polarization can arise, where this spin valley coupling is preserved in subparts of the system. And this is exactly what happens for TMDs, since the interlayer coupling is actually much weaker than the intrinsic energy scale. So it's much weaker than the spin orbit coupling, for instance. So this has actually been shown experimentally by Marcos in Eindhoven, where they measured the Kerr rotation of circularly polarized light when interacting with bulk samples of tungsten diselenide. And what they see is that despite the presence of inversion symmetry, this spin valley light coupling is preserved in each of the layers of the material. Right? So when you shine circularly polarized light into it, you'll still see some spin polarization being created, although you will see no valley polarization being created. So this gives rise to an electronic structure that looks like this, where you'll recognize some of the properties that you see in the monolayer already. Right? So now you do have some spin valley coupling in each of the layers, but they're opposite, therefore opposite case sides. Now again, these top states transform as wave functions with mj equals plus and minus 3/2, whereas the orange states transform as wave functions with mj equals plus and minus 1/2.
Carmen, you have a couple of minutes left.
Yes. So now if I look at the spin scattering processes, I will not look at the intra-layer spin scattering processes, because those are very similar to those of the monolayer, but I will look at the interlayer scattering processes, right? So now if I want to flip a spin up in the top layer into a spin down in the bottom layer, I can do that for the orange circled states with fields that transform as E, and those are electric and magnetic fields in the plane of the monolayer. And for the states transforming as mj equals plus and minus 3/2, since time reversal doesn't play a role anymore, now this flipping is actually allowed, and it's allowed with operators that transform as the A irreducible representation. And those are electric and magnetic fields out of the plane of the monolayer. So that actually means that for these systems with optically created spins, like Marcos has shown that it's possible to achieve, we can actually tune the degree of spin flipping processes happening between the layers with an electric field in plane for these states and out of plane for these states. So it would actually be very interesting to repeat Marco's experiment, but now in a device where we have a double-gated structure that allows us to tune this electric field across the TMD. So I hope I showed you that for monolayers, we can go through a very simple group theoretical approach to obtain the symmetries of the eigenstates, and those symmetries are very different for valence and conduction band states. So that will give different spin scattering mechanisms for electrons and holes. And this actually does lead to a large asymmetry between the behavior of dark and bright excitants, and that has been experimentally observed. Now for the bilayer, despite the presence of inversion symmetry, there's this hidden spin polarization allow us to create spins optically. And we can control the behavior of the spins via electric fields, both in plane, but most importantly, out of plane. So with this, I would like to end, and thank you very much for your attention.
Okay, thank you, Carmen, for your nice talk. Mario, do we have any questions in the chat?
Well, we do not have any questions for the moment, for the time being. So I would like to ask Carmen about how free you are to model TMDs with, or whatever, any materials with a different rotation angle between layers. Because I can assume that the very same thing you have now, you have a top layer and a bottom layer of the same TMD with a standard bilayer configuration. Are you able to try to replicate what, for example, Harry Herrera could be doing with these twisting magic angle bilayers?
Yeah, well, the approach we take is really, there is no computation in what I did here. It was all group theory and just looking at the symmetry of the crystal, and then based on these symmetries, obtaining the selection rules. I think in an ideal case where you can just draw this different stacking on a computer, you can still take a group theoretical approach, right? And that just reduces or expands the symmetry that you're looking at, and the unit cells are different and so on. But yeah, so I think it would be possible. I don't know if it would be the most efficient.
And just another last question. I think I'm getting a little bit saturated. How is the interaction, the daily interaction between a theorist and experimental group? How is it? How does it work? How is this kind of symbiosis going on?
To be honest, I am neither an expert on this, nor I am purely a theorist. I am actually working with localized defects in silicon carbide, both doing a little bit of group theory and mostly experiments. And well, since Marcos joined the group, we started talking. We realized that a lot of the symmetries were the same. And there were some very interesting things that I saw in localized defects that I started to think, okay, would they expand to TMD since it's the same symmetry and the same type of orbitals? And that's how we started with this project. So I am really walking the middle line. I'm doing both. I hope that we can measure on these systems soon. Marcos has a student that is working on these samples. But I'm really trying to walk the middle ground, yeah.
Okay, I think we have no time for more questions now. So thank you very much, Carmen, for your nice talk. If you can unshare your screen.
Stop share, yes.
Yeah, so our next speaker will be Daniel Vaquero from the University of Salamanca. Daniel, are you around?
Yes, I'm here. I'm going to share my screen.
Okay, the floor is yours.
Okay, thank you, Jorge, for the introduction. First of all, thanks for to the organization for giving me the opportunity to give this talk, in where I'm going to talk about the work that we have developed in the last year in the University of Salamanca, where we have investigated the excitonic transitions in a monolayer molybdenum disulfide phototransistor using a new technique to study these excitonic transitions, that is low temperature photocurrent spectroscopy. Here we have represented a schematic of the device, and here I have plotted the typical spectrum that we obtain using this technique, where we can observe different spectral features that I'm going to explain. To introduce, first of all, I'm going to introduce what is excitons and what are excitons and tryons, that are the principal spectral features that we have in our spectra. Exciton is a bound state that is formed in the materials. It's formed due to the bound state of electron in the conduction band and a hole in the valence band due to the Coulomb interaction, and this form a neutral quasi-particle. Here I have represented what is a tryon, that is formed when an electron binds to an exciton, and it's formed by two electrons in the conduction band and a hole in the valence band. This gives us a bound state that forms a charged quasi-particle. There are so many works that use TMD as a platform to study these phenomena, this exciton physics, and that's because transition metal bicalcoquillenides are 2D materials with these structures that we have seen in the before, and this gives them this band structure that is represented here with 6 valleys, and here we have the different optical direct transitions that we have in these materials. This splitting in the valence band is given due to the strong spin-orbit interaction that these materials have. And these two optical transitions gives us 2 excitonic transitions that are depicted here as A transition and B transition. So these TMDs are very interesting to study this exciton physics, also because they have large binding energies and lifetimes of the exciton states. And there are so many works in the literature to studying these phenomena. Here we have some examples of works that treat about these phenomena. And they use so many experimental techniques, as these ones, scanning tunneling spectroscopy, linear reflectance, absorbance, and the most used one that is photoluminescence. But there are only a few works that use photocurrent spectroscopy as the principal technique of their work. Here you can observe 2 of them that use photocurrent spectroscopy, and here you can observe the different spectra that they obtain. We observe here that the excitonic peaks in the spectrum are very broad, and this is a problem to fully resolve different excitonic transitions in the different spectra. So what we have done to improve the quality of the spectrum is to introduce the low temperature. So we have developed experimental setup where that we have a schematic here, And here we have the light source that is a supercontinuum laser plus a monochromator that allow us to select the excitation wavelength of the light. Here we have an optical chopper that allow us to modulate the excitation, the frequency of the excitation light. Here we have two telescoping lenses that allow us to collimate and focalize the light over the sample. And here we have the sample in this stage inside a closed cycle cryostat that is at temperature of 5K and in vacuum. Also, we have put a lamp and a CCD camera using these two beam splitters, and this CCD camera allow us to improve the alignment between the sample and the excitation light. In this zoom, we have represent the light that goes out from the light source. Here we have the beam of the monochromator, and this beam have a bandwidth of 40 millielectron volts. We use this large beam in order to illuminate the whole sample, and this gives us a very high bandwidth of the beam. But for us, the important part of this beam is the optically active zone of the device, that is between the drain and source of the phototransistor, and the sample acts as a secondary slit that gives us effective bandwidth of 0.2 millielectron volts, giving us a very high spectral resolution. Once we have the setup, we start our measurements by characterizing the electrical response of the device. Here in the figure A, we have a representation of our device, and we have marked here the two terminal electrical configuration of the measurements. Here in this zoom, we have the geometry of the contacts that are edge contacts and are done by titanium gold. And here we have in this zoom the structure of the two-dimensional phototransistor. In figure 1B, we observe the transfer curve of the device. We put here a source drain voltage fixed, and we apply different backlit voltage through the silicon that acts as the gate. And here we observe a clear N-type transistor behavior. When the backlit voltage goes over the threshold voltage, we have a very high increase of the conductivity. In figure C, we have the IV curves of the device for different gate voltages that are indicated here. And we have that the device have a saturation for high source drain voltage. This current saturation is provoked because we have Schottky contacts, and this gives us a behavior of a back-to-back Schottky diode. Also, we observe that the current saturation is not symmetric, and this is because the height of the barrier of the Schottky contacts are different, so we have an asymmetry. When we have done the electrical measurements, we pass to characterize the photoresponse of the device. And here we observe the the response of the device as a function of the time, and in resonance with the exciton in the exciton A at a frequency of 31.81 Hz. And we observe the on and off regions. And here we have what we call photocurrent. This increase of the current when the light is on over the device is what we call photocurrent. Once we know how the device behaves, we pass to perform the spectral measurements. Here we have a plot of a typical spectrum that we obtain in the monolayer disulfide phototransistor using low temperature photocurrent spectroscopy. And here we observe that we have with 5 spectral features plus an exponential background. We can fit very well our spectra. And these spectral features we related to neutral. We associate them to neutral excitons that are here A and B. Also, the charged excitons or tryons that are plotted in red. And we observe also some excited states of the excitons. And we are able to resolve all these peaks because we have a very low, very narrow peaks in the order of 80 milli-electron volts that allow us to see a lot of spectral features. These spectra can be modulated by the gate, and this occurs because modulating the gate we can change the carrier density in the conduction band, and this excess of carriers in the conduction band can produce efficient formation of charged excitons because we have a lot of electrons. So here we can observe that tryon A is enhanced because as a function of the increase of the gate. Here for the tryon B we observe the same behavior, and here of the excited states we observe that also can be changed using the backgate voltage. So once we have modulated the charged exciton between the excitons, we pass to the study of these excited states that appear for higher energies than the neutral excitons. We associate these excited states to Rydberg states, and that is because.
Honey, you have a couple of minutes left.
Okay, thanks. We have here the representation of the exciton, and it behaves like a 2D hydrogen atom, and this system have excited states that we call Rydberg states. In order to associate these excited states to the Rydberg states and do a correct labeling of the quantum number, these states appear in a very consistent way in all the measurements. As I was saying, in order to label these Rydberg states, we use an effective band model, an effective mass model, in where we solve the Schrödinger equation with this Hamiltonian, and we use a Keldysh potential. This Keldysh potential allows us to solve in a very correct way the different states, and we don't use a normal Coulomb potential because the excitons in 2D materials the electric field is very screened because of the environment of the phototransistor. So using this screen potential and these parameters that are the screen length and the electric constant, we are able to solve these, to perform a very good correlation between the theory and the experiments. Here we have the experimental data and the theoretical data. And we observe that the 2D hydrogen model that is solved using a Coulomb potential does not fit very well. We have here the fundamental optoelectronic of the fundamental optoelectronic parameters of the material. And here we observe that with these two work, we have a very good results that are very similar. But with this work is different, have different parameters. We attribute that to the atomic mislabeling of the different states. So, as a conclusion, to finish the presentation, we have developed a new experimental system to study excitonic transitions. We perform an observation of two different repeat series in the same spectra, and we have demonstrated that the simplicity and the power of this technique. As a future works, we can use this system to measure dark excitons in an easy way, and also the dark excitons that are spin forbidden transition and momentum forbidden transitions. And this setup can be adapted to investigate non-linear optics phenomena. Here is a summary of the presentation, and thank you for your attention.
Thank you very much, Daniel. We have time for one or two questions.
Yeah, for the moment, still no questions appearing. So if anyone is willing, nice time to. So Danny, what's next? So what do you think is going to be next with your setup? So now you've proven your setup, you can use it for example, dark exciton. So can you foresee what is going to happen in the next months, year of work? Materials,
yes,
example.
Our next work, in my opinion, have to be how to try to measure these dark excitons with this technique, because the only thing that we think that we have to do is tilt a little bit the sample respect with the excitation light, and this change of the direction of the electric field can provide us, can allow us to see these different states, these different dark exciton states. Looking in a long time, I think that this setup can be very well adapted to study non-linear optics in TMDs, but that work will be for the future.
Thank you, Dan. Thanks. I don't know if anybody else has a question for Daniel.
I do. I sent in the chat, but I just realized that I sent to Alberto.
Marcos, I didn't get it. Sorry.
But if I can ask, use my microphone.
Yeah, please go.
How do your results compare with the results from Tony Hines? So specifically the ones from the Rydberg's states that is shown there in the graph on the bottom. The bottom here. Right. Yeah, those. If you plot like your results extracted by the photocurrent spectra and the results obtained by I don't remember if it was with the two photon absorption or if it was reflectivity, because it had a very different values for different groups, but then the table went away very fast. So
this table, you mean, no?
Yeah, yeah.
For the group of Xavier Mariov and Bernard Urbasek in Toulouse, we have more or less the same results. They use in this work they use magnetophotoluminescence, and in this work they use only photoluminescence. Also,
but this progression of the Rydberg states was also measured. Is the same figure as the one on the top right there for monolayer TMDs, which was done by Tony, I think, some time ago.
I think that they use linear reflectance. But for monolayer molybdenum disulfide, that is this work of here, they use photoluminescence, room temperature photoluminescence, and I think that they have a mislabeling at the time to label the different quantum numbers in the states, because we have very different values in here, and we think that, but we are not sure at all.
Yeah, so if I can also say something, what we believe is that because they are measuring room temperature, the first excited state that they see is not actually the first excited state, but the second, and the first one is hidden below the tail of the ground state. So that's why we think that their values are different. We still have to do checks in other materials to make sure that we are doing everything all right. But our results seems to fit much better with other later results measured by other techniques, by magnetoresistance, for example. So we believe that we are doing it right.
Great, thanks.
Okay, so we have no time for more questions, so we will give the room for our next speaker. Please, Danny, can you unshare the screen?
Yes.
Thank you very much for your talk.
Thank you.
Okay, so our next speaker will be Andres Castellanos, our second invited speaker of today. Andres, are you around?
Hello, can you hear me okay?
Yeah, so
all right.
Whenever you want, the screen is yours.
Yeah, let's start screening. I hope that you can see now my screen.
Yeah, works beautifully.
Yeah, it works.
All right, so let's start then. Thank you, Jorge and Mario, for the invitation to participate in this colloquia. Today, I'm going to talk about, I'm going to change a little bit of gears. I'm going to talk about a mineral. There is a layered mineral, and it has a form of a superlattice. Okay, so it's kind of like a natural superlattice, let's call it. And I'm going to talk about how the interlayer interaction that is always known as a weak van der Waals forces in this kind of layer compounds, even though it's weak, is strong enough to break the symmetry of this natural superlattice. Okay, so this material I'm going to talk about is called Bandgap. As probably some of you know, sorry, I cannot now. As probably some of you know, I moved to the CSIC, the Spanish National Research Council, particularly to the Material Science Institute of Madrid, only 3 years ago, and thus I have to acknowledge the support of all my group members, current and past group members, especially my senior postdoc Ricardo Frisenda, and all the PhD students of the group, and our project manager, because they have helped us to basically ramp up with the new labs and setting up all the new equipment and characterizing and calibrating the new setups. Today's talk is going to be focused about basically this paper that has been published recently in I think in February, March, and I have to acknowledge basically the heroes of this story is our Ricardo Frisenda, that has been working on the optical properties of the optical measurements and the sample fabrication. Gabriel Sanchez Antolino, that has been working on the TEM characterization. Nikos Papadopoulos from TU Delft that has been working on the electrical transport, Paulina Plotzoka that has been doing the Raman characterization, Pablo San Jose that has done our theoretical support for this work. Let's start discussing about why to study van der Waals superlattice, and I think the motivation is based on like the beginning of this field of research on two-dimensional materials. Already from the very beginning, Kostya Novoselov and Andrei Gaim saw the possibilities that opens up when you start having control on the layers of these compounds materials. If you can stack layers on top of each other with a certain degree of control, you can open up new possibilities. And this is already said in the Nobel Prize lecture in 2010. And moreover, if we go back to, there is plenty of room at the bottom from Feynman, we can see that there is the very same concern there. So he was wondering what could happen if we have control on the layer structures and we arrange these layer structures with just the right layers. Okay, so this is already an old dream in nanotechnology that is nowadays possible with these two-dimensional materials. So basically this will be like the cartoon picture of these heterostructures. How do they look like? So we just place layers on top of each other, and superlattices are just a specific kind of heterostructuring where you can stack these layers in a periodic fashion. Okay, so you can stack A, B, A, B, A, B kind of two-dimensional materials on top of each other, forming a superlattice. So you can have a look to this perspective article we wrote this past year in 2019 about superlattices on van der Waals two-dimensional materials. And we explore different kind of superlattices. But this simple example will be just stacking the similar two-dimensional materials. Okay, when you see this kind of cartoon representation, it seems simple, but you have to take into account that these kind of heterostructures or superlattices, they are typically arranged in a kind of like manual fashion, using quite rudimentary tools. Okay, so basically like micro manipulators that you actuate with screws and optical microscopes, you know, to supervise that all the process is done properly. So even though like a PI will think about this kind of approach like an elegant, I have to say that students, they find it terribly cumbersome. Okay, so and I've suffered it myself. Of course, there are nowadays new ways of doing this kind of assembly. So some Japanese group has proposed a robotic setup in order to do this assembly of heterostructures. Looks like this, but we like to think about it in a more tender way, as our little robot piling stacks of materials on top of each other. But even though you have this robotic assembly, you will always find a problem with the interlayer adsorbates. When you do this kind of stacking process, there is a chance that you basically trap adsorbates in between the layers, and no matter what you do, you will get some of these bubbles or blisters. And depending on how good your transfer is, the density of these blisters will be larger or lower, but you will always get this kind of interlayer adsorbates. And for certain applications, the PI wants these heterostructures cleaner, right? Apart from the cleanliness, there is also the problem with the twisting angle. When you start piling layers on top of each other, so there is a chance that they are not perfectly aligned, right? So you have to have a certain degree of control on the twisting angle, because for certain physical applications, in order to observe certain physical phenomena, you want to have really, really well control on the twisting angle. So sometimes you want them perfectly aligned or with a small twisting angle. Sorry, like, you know, like controlling really well the alignment and maybe even including a little twisted angle, no? Like in the case of the twisted bilayer graphene that you will heard of in the plenary talk this afternoon. Okay, in order to get this kind of like really well controlled twisted angle samples, you need a lot of patience. Okay, so it's a terrible work. It's really difficult to get these kind of samples, and that is where naturally occurring minerals or layered minerals start to play a role here. So because we like to think about like these, you know, perfectly stacked layers as this deck of Spanish playing cards. And naturally occurring minerals are not just perfectly aligned, they're like brand new, okay? So they're like coming directly from the factory. So because we like to think about like the earth as a you know, the best mineral, the best crystal growing oven, and you can get all these minerals that they are layered just directly from minerals. Okay, so all these materials, they are layered compounds, and out of them we got interested in frankite, because frankite, well, it's a relatively new mineral, okay, but already from the 90s it was known that this mineral had a composition, a structural composition of alternating layers. So like pseudo tetragonal layer, so like quasi-cubic, let's say, pseudo hexagonal layer, pseudo tetragonal, pseudo hexagonal, pseudo tetragonal. So this kind of super lattice structure. Okay, so this compound here, this layer here, it resembles to galena, so lead sulfide, and this layer here is tin disulfide basically. So, and then you have these alternating layers of lead sulfide, tin sulfide, lead sulfide, tin sulfide, etc., etc. So this is already quite interesting. And once you have this superlattice, what can the interaction between the layers do to the superlattice? Because the idea of a superlattice is that just by assembling this periodic superstructure, so the properties of the compound has to be different than just some of the individual layers. Okay, and one of the first things that you have in this frankite is, for instance, you get a very narrow bandgap semiconductor. If you calculate the band structure with DFT, you get a really narrow bandgap. And this is shocking because a monolayer in sulfide has a bandgap of more than 2 electron volts. Okay, so this is already telling you that the superlattice is not just the sum of the two lattices. And also in this case here, you can see clearly how the electrons and the holes, they get separated in the different physical layers. Okay, the electrons prefer to stay in the tetragonal layers, and the holes, they prefer to stay in the hexagonal layers. We have seen in scanning spectroscopy measurements that this bandgap is indeed a quite narrow bandgap. And we have also done some liquid phase exfoliation in collaboration with Emilio Perez group. And we have done UV-Vis absorption. And we have seen that the material has non-negligible absorbance up to 3,000 nanometers, 3 microns. Okay, so well in the infrared part of the spectrum. And we even see this little peak here that we believe it's an exciton resonance in our system. All right. So is there anything else can do this interaction between the layers? And as I told you at the beginning, so I just told you already the highlight of talk, this weak van der Waals interaction can also break the symmetry of the system. So already in the 90s, so apart from the previous TM measurements I showed you, so there were other groups doing cross-sectional TM, and already in these early works in the 90s, they were seeing that frankite had these kind of like waves in the cross-section. Okay, this is kind of funny because the tetragonal layer and the hexagonal layers, they should be isotropic in plane. But, so the compound, the superlattice, has this anisotropy, so has these ripples. Okay, and we can even see if we do like top view TM instead of cross-sectional TM. So these are frankite flakes on top of holes of silicon nitride TM grade with holes. If we do this TM, this top view TM, we can see that indeed there are fringes with a period that matches with these waves that people have seen in the 90s. And in the diffraction pattern, we can clearly resolve the two different lattices, the hexagonal one and the pseudo tetragonal one. Our colleague Pablo San Jose made a model simple mechanical model, including the different terms, the interlayer interaction, the bending rigidity, the shear forces, etc., and found out that basically the interaction between the layers, the weak van der Waals forces between the layers, it was strong enough to distort the lattice of the two layers in order to commensurate these two lattices. Basically, the pseudo tetragonal and the hexagonal lattices, they have lattice parameters that they are making commensurate, so they cannot, fit to each other in order to make a nice moire pattern. But just by deforming slightly the layers in plane, they can commensurate, and that does reduce their energy, okay, and becoming more favorable. And therefore, basically, out of this model, what it says is that the most stable solution for the lattice is to have this spatially varying strain profile in plane. So basically, the atoms, they get expanded, compressed, expanded, compressed, expanded, compressed, in order to accommodate each other, these lattices, and commensurate. So basically, we start from a system in where when we stack the layers, they should be isotropic. And once they start to interact, basically the atoms start to move around a little bit in order to accommodate the two lattices. And they do that by breaking the symmetry of the system. Interestingly, our colleague Gabriel Sanchez-Antolino has seen, by analyzing these TM images very carefully, he could extract the position of the atoms in plane and actually map the strain in plane that these lattices are filling, and making a map of strain that matches very, very well with the strain profiles calculated by our colleague Pablo San Jose. So that therefore, so these systems are really having this spatially varying strain profile in order to reduce their energy. And interestingly, this kind of spatially varying strain, it's inducing a lot of anisotropies in the system that they were not present just in the, in the naive model that you place the hexagonal, tetragonal, hexagonal, tetragonal layers. In the nice cartoon in where you have just these layers on top of each other without interaction, these systems should not have any strong optical or electrical anisotropy. But once they start to interact and they develop this strain that varies on especially, then the system develops this optical and electrical anisotropy. For example, here you can see differential reflectance spectra taken with light that is linearly polarized, and we start rotating the polarization of the light. And what we see is that the differential reflectance has a maxima and a minima at certain positions. Okay, so we can see a polar plot here, and basically in this polar plot we have that the maxima position of the differential reflectance that corresponds to the maximum optical absorption of the system is almost perfectly aligned with the direction of these ripples that we see in the TEM. Okay, so this little difference here is within the experimental resolution that we have in the alignment between the two images. Okay, we have also done electrical transport measurements on these kind of samples, and what we have done is do electrodes that they're with different angles in order to test how is the conductivity at different crystalline directions of the system. And we see again that the conductance of the sample depends on the direction. Okay, so we probe at different directions, and we see here this sine wave here. Well, it's actually cosine square wave. And in a polar plot, you can see that it has this elongated shape. So there is indeed a clear in-play anisotropy. And actually this anisotropy again matches with the anisotropy that we see for the same flake on the differential reflectance, and matches with therefore with the position of these ripples. We have also measured Raman measurements with the help of our colleague Paulina Plotzoka in the CNRS in France, in Toulouse. And this Frankite system also shows a highly linearly polarized Raman emission. So basically we excite this sample with polarized light, and we use an analyzer, And then we can monitor the polarization dependence of these different peaks of the system. So we have basically, these are the 4 main peaks of Frankite, and we can see how these different peaks, they have a certain anisotropy that is closely related to the anisotropy that we see in the differential reflectance for the same flake. Okay, again, the little misalignment between the differential reflectance and the Raman measurements can be done by the experimental uncertainty on aligning the different samples in the different experimental setups. Okay, so I come almost to the end of the talk, and I want to basically wrap up saying that this so-called weak van der Waals interactions, so it's always known, it's believed that this van der Waals interaction between the layers, they're really weak, and they are typically neglected most of the time, but they are strong enough to deform the lattice in order to minimize the total energy of the system. And that leads to this, what we call the symmetry breakdown. So we pass from a layer that should be, in theory, neglecting the interlayer interaction, should be isotropic in plane, and we convert this layer into an anisotropic system in order to get these 2 lattices to get into the commensuration regime. And we have seen how this little change in the position of the atoms is strong enough in order to induce a lot of anisotropies in the system, optical anisotropy. So we have seen that the system it shows this linear dichroism. So basically, the absorption of the system depends on the orientation of the incoming linearly polarized light with the lattice. We have seen also electrical anisotropy and vibrational anisotropy. And moreover, the optical and electrical anisotropy, they are closely related. So what we see is that we have the higher absorption when the light is linearly polarized along the directions with high conductance. Okay, so similar, let's say, to the way wire polarizer works, basically. I want to stress that we had a lot of fun studying this Frankite so far, and it's because whenever you start studying a new material, you get, like always new things. You will observe always new physical phenomena that you were not expecting. No, like the case of the symmetry breaking, and layer minerals are particularly interesting. And so far, surprisingly enough, only a handful of them has been studied. Mostly graphite and molybdenite and some micas and clays. So there is also tungstenite, but it's really rare, and I think there are only like 1 or 2 papers on that, on natural tungstenite, let's say. But you have a full, class of layered minerals that almost nobody has explored so far. This is a picture of the Mineral Museum in Madrid. It's a picture. It's a real pity that you guys cannot come to the physical meeting in GEFES, and we have to do it online, because otherwise you could pass by this museum. This museum is very nice. And as an example, I put you another layer compound that has been barely explored. That is almost similar to Frankite, is called cylindrite. And another interesting thing about these minerals is that it's not just studying the mineral itself, it's learning something from the mineral and using it in the lab, right? So I put as an example, for instance, the cylindrite, because some groups, they have been working on actually mimicking the structure of cylindrite in order to make synthetic minerals, synthetic crystals, that they mimic this superlattice structure of cylindrite. There are even works from RSEF-GEFES in which they do this kind of what are called misfit compounds in order to make these microtubules, these nanotubes of misfit compounds. So we have a lot to learn from layer minerals, that we can get, let's say, unexpected physical phenomena from them, but we can also borrow something from them, like for instance learning something about the structure and copying in our labs. And with this, I already finished acknowledging the funding sources and thanking you for your attention. Thanks.
Thank you very much, Andres, for your nice presentation. Mario, do we have any questions in the chat?
Yeah, we have plenty of them. So we will start with a question from Alberto Cortijo. So how does strain changes the layer charge pattern that you mentioned in the beginning of this talk?
The charge pattern. Oh, yeah. I understand. Yeah, it's a difficult to know because basically, let me go to this. So basically, so I think Alberto is asking about this, right? So about how strain will change this. It's really difficult to know because this is kind of like the state-of-the-art DFT can be done on this system. This system, you can see, is very complicated. If you add to this system strain profile with periodicity of 4 nanometers, then the supercell is going to be humongous, okay? I think some little approximations could be done, but nobody has done it yet. I mean, I think the system is complicated enough to start, let's say, playing with it. But indeed, I mean, strain should completely change these electrical properties here, the band structure here, as we can see from the electrical conductance. I mean, we have seen that there is a direction where we have high electrical conductance and one direction where we have low electrical conductance. So completely sure the band structure has to change with the strain. I think the current models with DFT, they cannot account for it because of the complexity of the system.
Thank you. So we have more questions, guys, popping in. From Marcos Guimarães, we have a couple of them. The first one is, did you explore the gate dependence in these devices?
Yes, we have done some, sorry, I don't have it here. So we have fabricated some field effect devices with Frankite. No, I don't have it here, sorry. No, I don't have it here. But they're P-type, but they are strongly doped. So we cannot see the charge neutrality points. So they're basically, the conductance goes down as we increase the gate voltage, but in the typical gate voltage we work with, so let's say minus 60 to plus 60 volts, we change the conductance at 10% or more than that.
Okay, and could you comment a little bit on the evolution of the inbuilt strain as the number of layers go down?
We don't know. Honestly, we have no clue about it. So you mean about like these? Yeah. So it's a good question. We haven't tried. So I think like the thinner layers that we have measured, they are like let's say in all these measurements here in the electrical and optical and electrical measurement, the thinner layers that we have measured, they're like 10 unit cells. So I think we haven't measured anything thinner than that.
Carmen Gilardon is also asking about strain. So can you think about strain periodicity? So like a strain periodicity in plane as a lateral superlattice. So if yes, are the dimensions commensurate to what you need to create phononic or photonic guidance structures, for example?
So I will totally think of this periodic strain as a novel superlattice. So it will be a twofold superlattice in this case, because we have the superlattice, structural superlattice and the strain superlattice in plane. I totally agree. I haven't think of I mean, the period is around 4 nanometers, right? So it's around a little bit more than 4 nanometers. I haven't think of any application of this lattice yet. So I will give a think about it. Yeah.
And also, well, Pablo Ares was also commenting this probably, well, appearing to be a hot topic about the rippling. How does it change with the number of layers? So, well, people are pretty much interested in this.
Yeah, I mean, we don't know. So we should check samples that they are thinner, but it will be challenging. So typically the samples that they are thinner than 10 unit cells, they are very small in area. So we could maybe measure in TM or something like that, but making optical and electrical transport is going to be difficult. So we can maybe get some insight about the structural, rippling amplitude and so on, but getting an insight about how that affects to the electrical properties is probably challenging. But maybe we can get some insight about the periodicity amplitude. Yeah.
So one question also on my own. So did you mention that Paulina Prochorka was the one working with this Raman spectrum that you've taken and you've shown? So considering that she's working on a high magnetic field facility, have you applied any of these post-magnetic fields there?
Not yet. So we were planning to, because for instance, not with Frankite, but the cylindride, it has magnetic interactions even in the single unit cell limit, and we were planning to play with this family of materials at high magnetic fields. But in the meantime, I started collaborating with Paulina in this twisted transition metal dichalcogenides, moire patterns, and so on, and then we got distracted.
Thank you. I don't know. We have plenty of time for more questions. So I don't know if you have.
Yeah, I would like to ask some questions myself as well. Well, first of all, congratulations for the talk. It was really interesting. So one thing I always get curious about these naturally occurring heterostructures is when you measure transport on them. I guess when you exfoliate, depending on what is the top layer that you get right below the contacts, probably the transport is also going to look different, right?
Yes, that is a very good question. We have no clue about.
Okay.
So we have been, since we started working on this Frankite, we've been always wondering about how to get an insight about if there is a preferential top layer or not. So I mean, it could happen. So let's say if the material is completely stable, let's say, whenever you exfoliate, you will get 50% chances you get the tetragonal, 50% chances you get the hexagonal layers. But it can happen that whenever you expose one of them to air, it degrades. And then you get preferential of one layer. So those are the two scenarios, but we have not the right tools in order to test them.
Okay.
So we are still working on it. But let's say, I mean, it's just a curiosity, let's say, but yes, so it's an open question so far.
And then another question is about so when you do the polarized Raman measurements, you were seeing this modulation with the polarization, right? Were you able to identify the symmetry group by these measurements? And if so, does it match with the symmetry that you expect for the crystal itself?
I think not. If I remember correctly, so all these peaks, they are attributed to weird, really weird vibrations of the lattice, but it is all, let's say, hand waving arguments. So let's say if you can see, like from the literature, so you can find like these peaks attributed to some vibrations in the literature, but they are just simply because this one resembles the Raman mode of the galena, the lead sulfide mineral, and therefore we believe there is this vibration of the lead atoms against the sulfur atoms, wherever. But
so it's not clear what Raman modes they are.
All are hand waving arguments so far.
Okay.
Yeah.
All right. And also, I also get a bit puzzled with this rippling, because I find it somewhat counterintuitive that if you have to apply some strain to one lattice to put it on top of the other and perfectly match. I will imagine that it will either expand continuously or compress continuously along the whole crystal. I find it a bit puzzling that you get this strain modulation.
Not really. So it's similar to the example when, so I mean, like the backlight induced rippling, right? So it's similar to that problem. So remember the elastic substrate. You place the crystal on. You release the the strain, and then you get these ripples, and the ripples are tensile, compressive. Tensile, compressive is similar to that. It's
yeah, but then in that case, you are only applying the strain in one, how to say, so at the bottom of the layer, not at the top, right? But here it's sort of sandwiched, so
it's a
I don't know.
It's a competition between forces. It's similar to the other. So in the other problem, you have the competition between the bending rigidity and the adhesion force. And here it's basically the same, but you have to take into account also the shearing forces. That's,
okay.
But it's very similar to the other process.
Okay. All right. So if we don't have any more questions, we are actually a bit ahead of schedule. Yeah, I guess we can go for the next talk.
Okay, thank you.
Yeah, thank you very much, Andres. Okay, so our next talk is going to be by Sergio Puebla, also from the group of Andres Castellanos. Sergio, are you around?
Yeah, hello everyone. Do you hear me?
Yeah. Can you please
okay.
share screen?
Okay. Okay. So hello everyone. Thank you for attending this conference. I'm going to talk about in plane anisotropic optical and mechanical response in two-dimensional molybdenum trioxide flakes. So we are interested in this type of flakes. This molybdenum trioxide flakes phase is a van der Waals semiconductor, and it has a direct bandgap of 3 electron volts. It has been used as a buffer layer and as a whole structure in a different type of solar cells, or for example, of perovskite or silicon also, and had been used also in light emitting diodes. But what we are really interested right now, it's about its structure. Since it's a van der Waals layers, so it has a direction which atoms are going to be more separate, and it's a layer material, and but also it has an anisotropic in plane. So this plane group, you can get two type of notation, the PNMA type or the PBNM. So these two are really the same, but with a rotation matrix. And we use this one, which we place the v-axis in the perpendicular to the van der Waals gap, and the shorter directions we set the z-axis, and the longer direction we say that it is the a-axis. So also it has been some polaritons in van der Waals materials, and these polaritons have been seen that they are useful in array for cell, for example, and in infrared and terahertz detector. And for example, in this image, you can see a protein detector with a device made of fringes of graphene, and with the difference of frequency of plasma polaritons. When these proteins pass along these fringes, you can detect these proteins. These polaritons have been shown in this type of material. For example, here are studied two kind of modes of this material: the upper Resonant band, which is 983 centimeter to -1 and 893 centimeter to -1 Resonant band modes. And this is a technique used by Alonso González et al., which is called scattering and scanning near field optical microscopy, in which an AFM tip and metallizing AFM tip is illuminated with polarized light, and you can measure the polaritons. In fact, these are this is a disk of molybdenum trioxide. And these protons, you can see the interference of these protons with the edges of the flake, of the sample. And here you can see the dispersion of this flake, of these two bands, and you see this anisotropy dispersion with the two bands. In one it has an elliptic type of dispersion, and the other has an hyperbolic type of dispersion. But also, a month ago has been published this paper with Chen and Jarillo and their companions, in which they place slabs of molybdenum trioxide one top of another with different angles, and they say with the same technique, this polariton dispersion, these are real images, and they see this polariton dispersion, and they change the angle of the two slabs, and you can see the difference of dispersions along you are changing the angle of the two slabs from 0 to 90 degrees. And also they made this calculation. These are the Fourier transform of the real space. So it's the reciprocal space, where you are changing the angle of the two slabs. This dispersion are changing as well. So we see these methods. We see these experiments interesting enough to do some methods to calculate the thickness and to speed up the thickness identification and the symmetry identification of the crystal. For example, we have placed molybdenum trioxide flakes onto silicon dioxide substrate. In this case, it's 287 nanometers of silicon dioxide, and this you can identify the thickness of the flakes with the AFM, and then you can create a color bar which are going to be from a few nanometers to 100 nanometers of molybdenum trioxide, and it's going to be at different colors. And this dependent apparent color, you can use these color bars. These bars are from 88 nanometers of silicon dioxide to 297 nanometers of silicon dioxide. So it has got different colors for different substrates. And you can use these color bars to identify the thickness in a fast way with an uncertainty of ±3 nanometers. But also, you can see in this image a physical model. I'm using a Fresnel model with a spectrometer coupled with the optical microscope. You can measure the reflectivity intensity in your system, and you can calculate the optical contrast. This optical contrast, which can be calculated with this Fresnel model, it is shown in the C image, and these ones are of the same flakes. And as you can see, there's a little bit of offer between the two figures. It fits very well. In fact, this method has got an uncertainty of 1.2 nanometers for 287 nanometers of silicon dioxide substrate. These are the index of refractions and the station coefficients that we have been used in our calculations. And as you can see, this method to calculate the thickness is a reliable one, apart from that it is fast, because the Fresnel thickness calculated with this model and the AFM thickness measurement of the same flakes, they almost form some slope with one. In fact, this slope has the regression. You do a regression model, you get a slope of 1.02. So yeah, it fits very well, and pretty good. Apart from studying the thickness of the flakes, you can use this method to calculate the thickness and then use it for later slide I will see you. So we have already measured the crystal structure of, for example, this flake for some of them, but with a method called end-resolved Raman scattering, in which you use a Raman system with polarized light. Here you can see different peaks. We focus on 2 peaks of these molybdenum trioxide flakes, which are the AEC and the AEA modes, because they tell you the symmetry of the crystal. And with these ones, you can see the rotation of the flake that you're looking at. Here you can see the different peaks that from 0 to 90 degrees, this one decreases, and from 0 to 90 degrees, this increases. But apart from it, you can use a simple optical microscope with polarized light as well. And you can rotate this linear polarized light along the 360 degrees. And you can see a shift on the wavelength if you rotate this angle. Here is plotted with the stratigraphic plot. It is the difference of refraction index that you can you get along this angle. And with this method, you can also set which direction is belongs to the flake you're looking at. So the z-axis belongs to the direction of the highest refraction index. Also, we have studied the mechanical properties. We have studied them with the vacuum metrology method, which we have placed the molybdenum trioxide flakes onto PDMA's substrate, and we compress with a glass. We compress the PDMAs, and as you can see, these ripples they create in the flake and in the peaks. This is the color of the rest of the flake, and the valleys you can see a darker color. So looking at these ripples and doing these ripples along the 2 axes that we're interested in, you see that the profiles, the wavelength of the profiles along the two directions are different. In fact, the ripples along the A-axis are the shorter ones. And with this method, we can calculate the Young's modulus with this equation, and inserting this value that we have found in bibliography, or the Poisson's ratio that has been calculated by our theoretical group. We have found these values of Young's modulus on these 2 axes. And also we have done this with several flakes, and this is a scatter density plot with 14 different samples of molybdenum trioxide flakes, and fitting these samples to Gaussian function, it gives you this plot. So it could be a little bit more SDX, but it is very well performed. And you can compare these values with other ones published. For example, this one, you see that it differs a little bit, but the anisotropy ratio, which is the division of the Young's modulus of the z-axis over the a-axis, it goes between these two values. So we find this method a good one. So as a summary, we have found these methods to calculate the thickness of the molybdenum trioxide flakes. We think that it's a fast and reliable one. And we have found several methods to calculate the crystal orientation of these flakes. So these ones are, we think that can speed up the experimental, the experiments that are going to be made in the future. And also we have used this method to correlate with the mechanical properties of the materials. So thank you, everyone. I hope you have enjoyed this talk.
Thank you, Sergio. So if we do have any questions in the chat?
So for the moment, no questions, no.
Okay, let's give a couple of minutes just in case someone comes up with a question. Sergio, do you grow this material yourself?
Yeah, we have grown by ourselves in our laboratory. We get molybdenum foils, and we set these foils in an oven and in atmosphere air, and we heat up until 450 degrees Celsius. So the molybdenum trioxide flakes started to grow onto a silicon wafer that we have placed onto the molybdenum foil, and these flakes, then we transfer them with PDMS with a deterministic transfer setup onto the silicon dioxide substrate that we have already shown.
Okay, and do you always get the same crystal structure for the material, or does it depend somehow on the details of the fabrication?
Because we reach always the same structure, because this phase, this alpha phase, is the more stable. The more stable that in this kind of material, it has two phases more. But once you reach 450 degrees, all the phases that you have, if you have more than one, all of them get to this one.
Okay, well, thank you. Mario, there are still no more questions in the chat?
Okay.
No more questions.
Okay, so then we can go for the last speaker of today. Thank you very much, Sergio. Can you please share the screen?
Thank you.
Okay, so we are going to switch gears a little bit. Our last speaker of today is Pedro Vianney. He's going to talk about hierarchy modes in nonlinear liquids. So he's going to talk about 1D systems now. Sergio, are you around?
Yeah.
Okay. So whenever you want.
Share. Can everyone see my screen?
Yeah.
Yeah, okay. So, hello everyone. Thank you for the opportunity of presenting my work. So as you can see from the title of my talk, I'll be talking about how we use a momentum-resolved tunneling spectroscopy technique to map a hierarchy of modes in spinful nonlinear Luttinger liquids. So unlike most other speakers, I'll be talking about 1D, not 2D systems. So this is the outline of my talk. I'll just very briefly go through the Luttinger liquid model, as well as its nonlinear counterparts, in particular the mobile impurity model and the hierarchy of modes picture, even though this talk will be focused mostly on this theory. I'll then very briefly show how we use this magneto-tunneling spectroscopy technique to probe our 1D system, quickly present some run-on results of the TLL model at low energies, things like spin-shell separation, zero bias anomaly, but really what I want to focus on is this higher order replica modes. So the question is, can we observe interacting electrons? And we use 1D systems to do this really because well, we have both high correlations and strong interactions. And so personally, what I think makes 1D systems really fascinating is that even when you have modest or even weak interactions, you nevertheless have strong correlations due to geometrical confinement alone. And so if it's truly a 1D system, the electrons cannot pass each other, which means that any perturbation to the system has to be collective. There's no such thing as single particle excitations. Every single particle quantity you can think of really becomes meaningless. What this means is that the Fermi liquid theory is unstable, the theory breaks down, and in its place we have what's called the Tomonaga-Luttinger liquid model. Now, this theory has been going around for quite some years. Plenty of experimental evidence in favor of it, both in semiconductor quantum wires, carbon nanotubes, edge states, and more recently in cold atoms as well. And what's important to remember about this theory is that it makes two key approximations. First, it says that dispersion close to the Fermi points is linear, and this is a fair thing to say, assuming that you remain at low energies, so close to the points, but there's no reason to expect this approximation to hold at high energies. And the other one, and I'll come back to this in a second, it assumes an infinite length system. So on the theory side, there's been recently quite a lot of work done to try and deal with curve dispersion, and I want to highlight two of those nonlinear theories. The first one is the mobile impurity model. This was proposed by Vaquero and Glasman just about a decade ago, and quite recently we reported some experimental evidence. So this theory makes a clear prediction. It predicts a momentum-dependent power law, and quite recently we've reported evidence in favor of that. I won't be talking about that today. Instead, I want to talk about the hierarchy of modes picture. And what makes this theory unique really is that unlike both the linear Luttinger model and the mobile impurity model, so both theories assume an infinite length system, and the hierarchy of modes is really the first one to make a clear prediction on L, on length. It says that in addition to the main 1D mode, you should observe an emergence of higher order, they call them replicas, modes, and that this emergence should be to some extent controlled by system length. So the question is, can we observe this? So we use, like I said, momentum resolved magnetotunneling spectroscopy. What we do is we measure tunneling between two systems, and we know that the tunneling current is proportional to the overlap of the spectral function of the two. We can do this in a momentum resolved fashion, so by applying an in-plane magnetic field that allows us to give a boost in momentum, by applying a DC bias between the systems, same thing in energy. So here there's just an animation showing that. Here I'm showing 2D tunneling for clarity, even though the experiment I'll be showing in a second will be 1D 2D. And so for 2D systems, you know that so the Fermi surfaces are paraboloids, that's what you see here. Here you have the overlap between the two, this is proportional to the tunneling current, and here you have the dispersion map. So X is momentum, Y is energy. And really what you do is you can map both in momentum space by moving one surface with respect to the other, and then you can do the same thing in energy space. Now, like I said, we're not interested in 2D tunneling, we want to do 1D 2D tunneling, so the question now becomes, how do we create a 1D system? So we use a double quantum well gallium arsenide, aluminium gallium arsenide heterostructure. So essentially we have two quantum wells in close proximity. For reference, the tunneling barrier is roughly 80 nanometers thick. And these are some SEM micrographs of our device. And essentially what we do is, really the only thing I need to focus on here is this array of fingers. By laterally confining the 2D gas on the top well alone, we can squeeze this in 1D channels, and I'll show that dispersion in a moment. And then we can measure that to the bottom 2D layer, which acts as a probe, essentially. This is just another view of the device. As a quick side note, we came up with this technique, we call them air bridges. It gives us great flexibility in design. We've been able to fabricate, it's a very reliable technique. We've been able to fabricate up to 6,000 bridges on a chip without breaking any. So if anyone thinks this could aid their fabrication, I'd be happy to talk about this after. Anyway, so the important thing to know is that so we have two 2D systems in close proximity, and we have independent contact to each. So by appropriately biasing the gates, we can make sure that any current measured between source and drain has to result from tunneling, and then we laterally squeeze the top well alone into an array of 1D wires, and we can measure that to a well understood 2D system. So this is what our wires look like. So here you see the 2D band, and once the voltage becomes negative enough, you start seeing multiple 1D subbands, anywhere from 3 up to 4. Of course, by changing the geometry, you can change this number. We've fabricated a device up to 7 subbands, 1D subbands, that is. From here, you can extract densities, both 1D and 2D. And the important thing to notice here, well, two things. First one, here you have the red curve. This is the 2D density below the wires in the bottom well, and the same thing, we call it P region, but it's essentially the injection region into the wires, which is 2D in nature. And you can see that they closely match. What this tells us is that the bottom well even though we're modulating the top well, the bottom well remains relatively unperturbed, and as such, it can be used as a well-understood probe. On the other hand, on the top well, you see the 1D density. By varying the gate voltage, you can change both the 1D density in each subband as well as progressively occupy more subbands. So you can go from 1 to 2 to 3, or you can pinch off the wires if you want. So just to summarize, we observe multiple 1D subbands, anywhere from 3 to 4 for these devices. The 2D lower well remains largely unaffected by the surface gates, and the 1D density varies from 15 to 55 electrons per micron. That corresponds to an RS factor, so the ratio of the Coulomb to the kinetic energy, just below 2 to just above, just below 1 to just above 2 for what I'm going to show today, though even right now we've been able to push this up to 3. So these are what our tunneling dispersion maps look like. So again, X is momentum, Y is energy. Here you have the two conductance differentials, both along bias and field. And of course, we can look at this, and from here we can immediately extract well-understood linear Luttinger features, things like zero bias anomaly, spin shell separation. So that's what you see here, same data, just different color scale for clarity. And so the blue dashed line, really, that's just parasitic signal which we can subtract. The black dashed line is the 2D system, the bottom well, as mapped by the 1D system. Everything else is the 1D system. So this feature here, that feature there, that's the 1D system. We can fit this with parabolas and extract the masses, both of the spin-on and the hold-on. We can do the same thing by looking at spin shell separation at low bias, allows us to extract the velocities. So if we start collecting statistics on this, so from the hold-on and spin-on effective masses, we can relate this to the Luttinger parameters. We can do the same thing for velocities, and from there we can estimate the interaction strength. And that's really what we're doing here. So collecting statistics for a bunch of devices, you see that the RS, which goes back to the 1D density, can be varied from 1 to just above 2. And we can tune the interaction strength in our system from just above 0.5 to just below the non-interacting limit. So essentially we have a tunable 1D system which we can play with, and now by appropriately setting the gate voltage, we can map it at different configurations, and also we fabricated devices from 1 micron wires up to, well, here shown 5, but we've also fabricated up to 18. So back to the data I showed before. Here you have some simulated data, assuming, so tunneling between a 1D and a 2D system, but assuming a non-interacting 1D system. And what I want to focus on now is 3 regions in particular, which I've marked A, B, and C, and compare that with what's predicted to by the hierarchy of modes fiction. And really, if you start looking at the data, you see that in addition to the primary 1D mode, there's sort of a mirror image of that at positive bias, which is not predicted in a non-interacting model. So we first reported this back in 2016. We called it an inverted spin-on shadow band, where you can see the main 1D mode here and sort of a mirror image at positive bias. But what we've done now is systematically collect statistics on this for a variety of lengths. And so if you start looking at the longer wires data, so the dotted line here is the mirror of the dashed line. They're symmetric because there's a capacitance correction, but other than that, this will be the shadow band. And then you have the black dashed line, which is the 2D mode as mapped by the 1D system. And so if you look at 10 and 18 microns, really that feature is following the black dashed line. But once you start going to 5 microns or below, it's no longer following the dashed line, it's following the dotted line, and consistent with what we expect from the hierarchy of modes picture. So we concluded that this would be a first level excitation, mirror image to the main 1D mode at low bias. We then looked in a second region, what we marked here B, which would correspond to this B1B excitation, so now a second level excitation. That's what's shown here. So the first column is the dg/dv differential, so differential along y. The second column is same thing, second order differential. And the third are line cuts in this region. The magenta crosses follow the magenta dashed line, and the blue pluses this feature here. I find it easy if you start looking bottom up, but so bottom up, as you decrease in length from 5 to 1 micron, you see that there's a very faint feature here, but as you start going to smaller and smaller devices, something else starts to emerge. And in particular, if you look at the raw data, you see the main peak, but instead of directly falling to 0, instead there's sort of a shoulder feature to its left. This dies away very quickly in field, but also it gets stronger as you go to shorter and shorter devices, again, consistent with a hierarchy mode picture for second level excitation. So we found structure resembling both first and second level excitations. We know the 1D density, so from there we can estimate, according to the hierarchy of modes picture, what the spectral weight should be. This is something of the order of 10 to the minus 4, which is above the noise level of our experiment. So far, everything consistent. What we've also done is now focusing on a 1 micron device, but instead what we're doing here is we're changing the Y-gate voltage. So what we're doing is squeezing the channel more or less. So if you squeeze them enough, they stop conducting, you pinch them off, that's what you have here. But as you start slightly opening there, you see that something else starts to emerge. And again, because this is responding to Y-gate, not P-gate, or well, from the injection region, what this means is that we know this is coming from the 1D region. It couldn't be coming from the parasitic 2D signal. As one last thing to this data, if you look carefully at negative bias, there's sort of a kink here. This wouldn't be cost for much, warranted only observed for 1 micron devices. And if so, 2 replicas are clearly visible, but if you want to be optimistic, this could be evidence of a third replica as a shadow band to the second level replica. It seems to show some response to the Y-gate. Of course, that in order to be sure, we would have to go to submicron lens, which we haven't done yet. But of course, once you go submicron, at some point you need to ask yourself, when does it stop being a quantum wire and becomes a QPC? Anyway, 2 replicas in the data which seem to emerge as a function of length. So, like I said, we can change the confinement in our wires. We can tune up and down the finger, so we can change both the density, that allows us to change interaction strength, but we can also change the number of subband that are occupied. So everything that I've showed so far was in the single subband regime, but nothing stops us from populating 3, 4, 2 subbands. That's what's done here. So again, this is the same region as shown before, the second level replica, but what we're doing, this is for multiple subbands. That allows us to change the interaction strength all the way from 0.6 to essentially non-interacting system. Here, the magenta line is the extension. So you see spin charge separation is here, and the magenta line is the extension of that towards positive bias, while the green dashed line is the extension of the spin-on mode. And what you see is that for 1 and 2 subbands, clearly 2 features are branching off away from the Fermi points, and they can be separately resolved. For 3 subbands, you can't separately resolve them, but there is some broadening there. Again, consistent with this replica is just, for this particular configuration, it's too close to be able to separate it from the spin-on mode. And the same thing for 4 subbands, of course, here, they're essentially overlapping. But what we see is that this is responding to, the replicas remain even when we populate more subbands, and it's also responding to the interaction strength. And this is very interesting because all the theory is done assuming only 1 subband is occupied. And the reason for this is because, well, you expect that once more subbands start being occupied, the 1D approximation could start breaking down. The fact that we don't observe this seems to suggest that essentially our 1D systems, each 1D subband is sort of independent of each other. They have very weak coupling between them. And as such, we can add multiple 1D systems sort of in parallel. So just to conclude, we've shown a hierarchy of mode emerges in system of interacting fermions in 1 dimension at high energies. This is in clear contrast to what is predicted both by Fermi liquid and also by the linear Luttinger liquid model. This is consistent with the model proposed by Tsipliatev, the hierarchy of modes picture, where this modes should emerge as a function of system length. We've observed a first level replica at low field, the inverted spin-on shadow band. We've also observed the second replica at higher fields, a second level spin-on replica, which dies quickly away in momentum. If you want to be optimistic, hint of a third replica as well. And then these replicas remain even when multiple 1D subbands are occupied and their strength varying with G. So that's it. Thank you for your time. Be happy to answer any questions. Thank you.
Thank you very much, Pedro. So Mario, is there any question in the chat?
Yeah, enough, not known for the moment, but I would really much appreciate if Pedro could comment a little bit more how do you just produce, grow, fabricate these systems, please. Could you just please comment on them?
We fabricate this.
Yes. So how you just go to that, because you just start with a two double quantum world probably.
Yes, but we fabricate the devices, or how do we create the 1D systems?
Well, a little bit of both.
Okay.
So is it like a wet etching technique? So you just get the MDE wafer?
So essentially, the first stage is pretty straightforward, meso omics, and we have a first 1D E-beam stage to fabricate all these gates. We've had trouble with this mid gate here that kept breaking. You need to make sure that it goes into the split gate, so that we need to, essentially the mid gate here in green, split gate in red, and the barrier gate in purple. You need this in order to ensure that you have tunneling. Otherwise, you can't have independent ohmic contacts. The C gate here wasn't used in this experiment, but essentially what this allows us to do is that instead, if you want to measure tunneling across the top layer alone and stop the tunneling, you can open this gate. But we didn't use this for this experiment. So that's the first E-beam stage. The second E-beam stage, you need a 3-layer resist stack, which need to be very well calibrated in terms of thickness to fabricate these bridges. Now, the good thing about these bridges is that once your calibration is good, and it took me about 2 months to get that calibration right, it's incredibly reliable technique. So you can see under optical microscope if the bridges are there. They very rarely break. It's either everything's broken or nothing's broken. And we've been able to fabricate in different devices up to 6,000 bridges in the same chip with all of them connected. And it's a really nice thing to do because essentially, before we had this, we had to come up with very creative geometries of getting this tunneling right and getting the rates around each other. Now we don't need that because we can just go over the gates instead of going around. And it also allows us to have more gates. So it allows us to introduce this B gate here. So like I said, the 1D region is in here, but in order to inject current into the wires, you have this 2D region. And by having a gate there, you can sort of move this region around and you can map it separately and you can subtract it from the data. So we can only look at our 1D, 2D tone signal instead of having this parasitic signal on. And that was an improvement we were able to do because of this gate here. So it's essentially 2 E-beam stages. First one for the surface gate, second one for the air bridges. And then, to create the 1D wires, what you do is you'll actually squeeze the channels and you can vary that to essentially play with how strong the interactions are. By properly balancing the gates, you can make sure that you're only injecting in the top well, goes into a 1D system, tunnels into your 2D, and goes to the drain. It's very easy to know if this is not working because essentially this is of the order of mega ohms resistance, this is of the order of kilo ohms. So your conductance just shoots up if some of this starts leaking. So we're fairly confident we have 1D, 2D tunneling, and we can play with this with some flexibility, and then essentially, like I showed here, gives us a tunable 1D system.
Yeah, thank you so much.
Yeah, well, if there are no more questions, then I think we can finish the session already. So thank you very much for the nice talk. And thank you to all the speakers for being here and to all the attendants for being here as well. We have had, during the whole session, around 30 to 40 attendants. So I think it's quite successful for an online meeting. With this, I hope you have enjoyed the session, and I hope to see you all tomorrow. We have Chelsea Slim opening the second session of this mini-colloquium at 9:30. So I hope to see you all here. Thank you very much. Oh, as a final comment, as I said, the session will stay open until 1:30. So if you want to use the chat to ask some questions that were left during the talks, or to just comment something with the other people connected, feel free to do it.
Hi, Jorge.
Yeah, I'm here.
Isn't it better if we could also, yeah, okay, great. I was gonna say that we could also turn on
Yeah, exactly that.
the cameras, so have
Yeah.
have more people. I'll turn on my camera right now. I'll also send you down here. I had a question. I think was the work that you were involved there. Forgot the name. I think was Daniel was presenting. That you also mentioned that you're planning to do non-linear to study non-linear optical response using the photocurrent technique.
Yeah, so I guess you already know where we are headed with this, right? So the idea is to do this these photocurrent measurements for circular photogalvanic effects, photon drag effects, and so on and so forth. But the idea is now to try to look for somewhat more interesting systems than just transition metal dechalcogenides. So either switching to another 2D material with lower symmetry, or trying to alter the symmetry of the TMDs, applying strain or with some other trick. So in the mid to long term, that's sort of the idea.
And there's to look for two photon absorption or kind of something like that, or what do you mean by non-linear?
Well, yeah, non-linear in our case is non-linear optoelectronics. So, well, we could look also for things like the second harmonic generation to photon absorption or so on. But that, I think, with our method of measurement is trickier because, well, in the case of second harmonic generation, the energy, well, the frequency at which we will see a signal will probably be too high to measure, right?
There,
yeah,
if you go like to the IR, what would be something in the, I think, more towards the 1,000, or actually lower, maybe even to see the excellent peak in the two photon absorption. So that might be something worth trying.
Yeah, that could be an option, but then definitely we have to switch to, well, to other material, or well, I am not completely sure about how does the light absorption look like in TMDs for the infrared, or the far infrared range. But yeah, that's another possibility. So basically, right now we have a system where we can, we are right now limited to visible light and near infrared because of the excitation source that we are using. But another part of the group is also working very well, from a long time ago in terahertz technologies. So we also have terahertz sources that we can more or less easily put in to use as excitation. Yeah, so that's another possibility that we are willing to look into.
Cool. Maybe you can also discuss later.
Yeah, that's probably okay. So as I said, the session will stay open, but myself, I have to go. I have another meeting in a few minutes. So again, thank you very much for being there, and hope to see you tomorrow.
Thanks, Jorge.
Bye.
Yeah, thank you everyone.